All right, so this video is going to be on substituted benzenes, and then we're going to talk a little bit about their effect on the benzene's nucleophilicity. So, is it a stronger nucleophile, or is it a weaker nucleophile, or maybe it doesn't have an effect at all? So the effects that we need to talk about are inductive and resonance effects. So they change the electron density in the benzene ring, right? We know these concepts, so this should be easy to follow. But basically the inductive effects is based on the electronegativity and the polarizability of the substituent. Okay, so let's go ahead and draw something out for you. We have an NH2, or we have an OH, for example. Now we all know that the nitrogen and the oxygen are more electronegative than the carbon, and so via inductive effects that would withdraw electron density from the benzene ring, as opposed to an alkyl group that would donate electron density into a ring. And we've seen this type of stabilization before, and it's basically we would attribute that as an example of polarizability. Those alkyl groups are polarizable, and so it allows them to donate electrons, okay? So the resonance effects. So resonance, this is where it gets kind of interesting, because that same nitrogen that withdrew electron density inductively can also donate electron density with its lone pair. And we can see that we can draw a resonance structure where we have a negative charge on the ring in the ortho position, right? You can do another resonance structure where it puts it at the para position and the other ortho, right? The alkyl group, there's nothing from the outside, outside the ring, and so there's really nothing going on in terms of resonance, okay? Now, when we have this carbonyl group, we can draw a resonance structure the opposite direction. So there's no lone pair to donate into the ring, but that oxygen in the carbonyl group can kind of accept electrons and withdraw electron density from that benzene ring. Okay, and it puts a positive charge at the ortho position instead of a negative charge like the nitrogen. So that red ring is electron rich from the nitrogen, and the blue ring is electron poor from the carbonyl group. And via resonance, that nitrogen was an electron donating group, and the carbonyl group was an electron withdrawing group. Okay, so let's take a look at a couple examples. Let's see if you can determine if they are electron withdrawing or electron donating groups. Okay, so that guy, we have a resonance structure for each of them. One goes into the ring, putting a negative charge at the ortho position, at least the one resonance structure that we've drawn, while the carbonyl group puts a positive charge at the ortho position, the single resonance structure that we've drawn. So the methoxy, the OCH3, is an electron donating group, while the carbonyl group, the aldehyde, is an electron withdrawing group. And so this is with respect to resonance, right? So we did talk about inductive effect versus resonance effect, and we saw that the nitrogen can do both, right? So which one dominates? Is it going to be resonance, or is it going to be inductive effects? So let's talk about that. So I'll give you a couple examples first, and then we'll definitely see it. We'll have a chart later that's more comprehensive. But for now, just to break it down with respect to resonance or inductive effects, when we have an R group, it only inductively donates, right? We didn't have a resonance structure for this, so it's electron-rich ring. This is an electron donating group. While the NH2, right, we had the electron withdrawing effect inductively, but then we also had the resonance structure where we can donate into the ring, and the resonance dominates when it comes to this, and so the electron-rich ring is the result, okay? Now, another example would be a halogen, right? So we have a chlorine there, or we could have an iodine, or fluorine, or bromine. Now, these rings, we still have a lone pair, right? So technically that can do resonance with the ring, and that would make it an electron donating group in that aspect with respect to resonance. But inductive effects dominate for halogens because we know those are very electronegative atoms, and so as a result, the ring is electron poor. Want to make a note also, sorry, the nitrogen, you can substitute that for an oxygen, right? We already saw that kind of comparison up above. And so as I mentioned also, the chlorine can also, we can relate that to bromine as well, even iodine and fluorine, but most often you'll see chlorine and bromine because those are the easiest to use when we're doing electrophilic aromatic substitution. All right, so the carbonyl group, we already see the electron withdrawing effect from the carbonyl group, the delta positive on the carbon because that electronegative oxygen, and then we also saw that resonance structure that withdrew electron density. So not only do we have a delta positive carbon, inductive effects, but we also have a resonance structure where we put a positive charge on that ortho position, and it can be shuffled around the ring, so it goes around the ring, and it's an electron poor ring. Okay, so that's basically, I think the only one that might be confusing is the halogens when it comes to being an electron donating group or an electron withdrawing group. Okay, but as long as you remember halogens are electronegative, then we're good to go. And then resonance usually wins. Okay, otherwise, when it comes to donating or withdrawing electron density. So let's talk about kind of the general idea of electron donating groups and electron withdrawing groups. Okay, so we'll classify them real quick for you. I'm drawing the red ones as electron donating groups because red, again, as you know, I like to associate with electron density. It's like angry. Electrons are angry, right? So we've got Z where N is O or oxygen, or wow, Z where is nitrogen or oxygen, sorry, and then we have an R group, right? Those are the two general, most common ones, I guess. And then, so those are going to be electron donating groups. Electron withdrawing groups are going to have a halogen, or they're going to have, we'll just put the Y for our atom, where Y is a partially positive atom or delta positive, or it's just a straight up positive atom. Okay, so it's got a formal charge of +1 or a partial +1. Okay, now what you guys know about Willie Mays Hayes? What do you think he's doing right now? Getting some batting practice right now? He's getting batting practice in? See, it's all in the hips. So let's do some practice real quick, because we definitely need to see a lot of these in order to really understand like the electron donating or electron withdrawing groups, right? So just so you know, EDG, electron donating group, EWG, electron withdrawing group. Magic, right? So let's draw out, I'm about to draw out like a bunch. I don't know how many. I'm just going to keep drawing, and I want you to write them down and then try and figure out whether or not they are electron donating groups or electron withdrawing groups. And then match your answers with me after you've paused the video and done them, okay? Let's see. Iodine, yeah, let's do iodine. Throw a little chicken foot in there. You can never get enough chicken feet in chemistry. We have an amide here. Let's see. Might as well throw in ammonium, right? Okay. So let's see. Let's do one more. That'll be good. Now pause the video and then see if you can match mine. So, as I said before, electron donating groups I'm going to make red. Electron withdrawing groups I'm going to make blue. So, let's take a look-see at the methoxy. Heyo. Got lone pairs on that oxygen. Remember, it is an oxygen, right? We said nitrogen or oxygen, and it's directly bound to the ring, and it's going to be an electron donating group, right? Because it can donate its lone pairs and put that negative charge on the benzene ring. A carbon and a carbonyl group is delta positive, so there's your Y atom. But it also, you can see a resonance structure where we would withdraw electron density, putting a negative charge on the oxygen, and then a positive charge in the ring. Okay, so that's an electron withdrawing group, EWG. Okay, check it out. There's our Y, there's our delta positive. Obviously, you have to imagine other things can be bound to that Y atom, right? So, as for example, the oxygen and the methyl group on there. So, it's a carbonyl group in this example. Now let's take a look at the next guy. So we do have a carbonyl group on that ring, kinda, delta positive, right? But we also have this oxygen here as like a little spacer. So what do you think it is? Boom. We're donating electron density into the ring, right? Well, the cool thing about this oxygen is that it could donate electron density to the carbonyl group too. So there's just multiple resonance structures with this guy. That makes it still, I'm gonna draw this in pink just to differentiate the green arrows, right? It is still an electron donating group because you have a resonance structure with with a negative charge in the ring, but it's not going to be as good at donating electron density into the ring as that methoxy would be, right? That OCH3, because it's being pulled in two different directions, right? It's going to the left into the ring or to the right into the carbonyl, and so it's just like, okay, not donating. What about this cyano group? You got the CN. We got the positive on the carbon, negative on the nitrogen. We can rewrite this to make it easier to understand as a triple bond, right? That nitrogen is still net delta negative. But if we drew a resonance structure where we pull one of those pi bonds and put it on the nitrogen, that puts a straight up positive charge on that carbon, right? And so even before we did that, it was already delta positive, which is the Y atom, and it's an electron withdrawing group, okay? So that one's pretty tricky for people because you usually see it with a CN, okay? This electron withdrawing iodine, that's easy peasy, right? We're on our way to the chicken foot. Chicken foot, we also know as an electron donating group, right? Got all those CHs and stuff, just donating, being awesome. It's an electron donating group, okay? Now check out this amide. Same thing as the ester above. That nitrogen can donate into the carbonyl group, but it can also donate red into the ring, right? And that makes it an electron donating group because we put a negative charge on that benzene ring, okay? Just like the ester. Now this reminds me of a common, kind of like a tricky question. Not tricky, just like y'all gotta understand what you're doing, right? So let's say we flip the script on you and put the nitrogen on not next to the ring but to the side of the ring. Or like, is it still an amide attached to the benzene ring, right? This is still an ester attached to the benzene ring. Before it was an electron donating group, but these guys, these are electron withdrawing groups. Now why is that? Because the N and the O atoms are no longer directly bound to the benzene ring. They are the Y atom, the carbon that's delta positive, is bound to that benzene ring now. And you can no longer draw a resonance structure that puts into the ring, but you can draw one where it withdraws electron density. So that would be the Y atom. So remember that. Those are some good ones right there. Electron withdrawing group, of course, for the ammonium, because it's straight up positive. Now that NO2, you got to redraw to really see it like clear. That nitrogen atom has a straight up positive charge on it if you drew the Lewis structure. So that's an electron withdrawing group. Do not be mistaken, because that nitrogen typically donates into the ring, right? But that would be one of the exceptions where you got a straight up positive charge on it, just like the ammonium, okay? So these are just some examples. These are some great examples though, so you should definitely write these down. Take a picture, put, like, I don't know, draw it on your mirror or something while you brush your teeth, take a look-see. But that's pretty much it. I'm gonna go ahead and finish this video here. That way the next video we can talk about the effects of these electron withdrawing group on the reactivity of these benzene rings. So that next video will be all about EAS with substituted benzene rings. Check it out.